Hi, welcome back to my class in Differential Calculus or Calculus 1. Today we will complete our limit theorems and we will apply them in obtaining the derivative of a function. And for those of you who missed the first 4 lessons in Differential Calculus, please search for my videos Art Teaches Calculus 1, Differential Calculus. Last time we have already stated 7 limit theorems. So today we start with the 8th limit theorem. Theorem 8 states the limit of a product is equal to the product of the limits. In this theorem, we are given two functions denoted by f1 sub x and f2 sub x. And we want to get the limit of the product of these two limits as x approaches a. And this theorem 8 states that the limit of the product of the functions f sub 1 of x and f sub 2 of x as x approaches a is equal to the limit of the first function f sub 1 of x as x approaches a multiplied by the limit of the second function f sub 2 of x as x approaches a. We apply this theorem 8 for the limit of a product to this example 1. Evaluate this limit. Again, to evaluate is to find the value of the limit of the given function as x approaches a specified number. In this example, we want to find the limit of the product of x and sine of x as x approaches a. So here x is never equal to 0, but x is approaching 0. In limit theorem 8, your f sub 1 of x is x. Your second function f sub 2 of x is sine of 1 over x. Applying theorem 8 for the limit of a product of two functions, this is equal to the limit of the first function x as x approaches a. Limit of x as x approaches 0 multiply by the limit of sine of 1 over x as x approaches 0. Multiply by limit of sine of 1 over x as x approaches 0. The limit of the first factor x, the limit of this first factor, limit of x as x approaches 0 is 0. And 0 multiplied by the limit of sine of 1 over x as x approaches 0, whatever this number is, will give us a product of 0. Hence, the right-hand side is equal to 0 multiplied by the limit of sine of 1 over x as x approaches 0. If the limit of sine over 1 over x as x approaches 0 is not equal to 0, and multiply it by 0 will give us a product of 0. Hence, the limit of the product of x times sine of 1 over x as x approaches 0 by limit theorem 8 is equal to the product of the limit of x as x approaches a, x is the first function, times the limit of the second function sine of 1 over x, limit of sine of 1 over x as x approaches 0. And we evaluate each limit. The limit of x as x approaches 0 is 0. And if this limit exists multiplied by 0 will give us 0. We take another example for applying limit theorem 8 or the limit of a product. Example 2, evaluate limit of ln of x multiplied by quantity ln of x minus 2x to the power 3 as x approaches 1. In the given limit, we have a product of two functions. This is the first function ln of x. And the second function is the cube of ln of x minus 2x. So to evaluate or to find the value of this limit, we apply limit theorem 8 or the limit for the limit of a product of two functions. And by that limit theorem 8, this limit is equal to the limit of the first function ln of x as x approaches 1 multiplied by the limit of the second function multiplied by the limit of the cube of ln of x minus 2x. ln of x minus 2x cube as x approaches 1. To evaluate each limit, we simply replace x with 1. And the first factor, the limit of ln of x as x approaches 1 is equal to ln of 1. And the limit of the second factor is obtained by replacing x with 1. Replace x with 1 and we get ln of 1 minus 2 multiplied by 1. Negative 2 multiplied by 1 is negative 2 to the power 3. And using your calculator, you can check that ln of 1 is equal to 0. Multiplied by ln of 1 is 0 minus 2 to the power 3. And this number, 0 minus 2 to the power 3 multiplied by 0 is 0. Thus, the limit of this given product of functions ln of x and the cube of ln of x minus 2x as x approaches 1 is equal to 0. Now we state the ninth limit theorem. It's for the limit of a quotient of two functions. We have the function f sub 1x divided by second function f sub 2 of x. Hence, this limit theorem is known as the limit of a quotient. And this theorem says that the limit of a quotient is equal to the quotient of the limits. That is the limit of f sub 1 of x divided by f sub 2 of x as x approaches a is equal to the limit of the first function in the numerator, limit of f sub 1 of x as x approaches a divided by the limit of the function in the denominator, f sub 2 of x, or limit of f sub 2 of x as x approaches a. But there is a condition in using this limit theorem 9. It says that the condition says that the limit of the function f sub 2 of x as x approaches a must not be equal to 0. Because if the limit of f sub 2 of x as x approaches a becomes 0, you will get limit of f sub 1 of x as x approaches a divided by 0, which is not defined or undefined. And if that happens, if the limit of f sub 1 of x as x approaches a exists, but the limit of f sub 2 of x as x approaches a is 0, then you conclude that the limit of f sub 1 of x over f sub 2 of x as x approaches a does not exist. We will take an example for that, but first we take an example for applying limit theorem 9, the limit of a quotient of two functions. We now take examples for applying limit theorem 9, or the limit for quotient of two functions. Evaluate, that means find the limit of the given function. In number 1, we are given limit of x squared, the quotient of x squared minus 9, divided by x plus 3, as x approaches 5. This is an example of a rational algebraic expression, where the numerator is an algebraic expression and denominator is an algebraic expression. Before you apply the limit theorem 9, or the theorem of a quotient of two functions, you check if the given rational algebraic expression can be simplified by factoring out the numerator and or the denominator. The denominator is linear x plus 3. The numerator is a quadratic expression, x squared minus 9, and we have a difference of the square of x and the square of 9. Hence, the numerator can be factored by using the special rule for factoring of difference of two squares. And we write number 1 as the limit as x approaches 5 from algebra. The factors of the difference of two squares such that the difference of a square and b square are a plus b and a minus b. We apply this rule for factoring the difference of two squares to the numerator, where your a is x, and 9 can be written as the square of 3. Hence, your b is 3, and the factors of the difference of x squared and 3 squared are x plus 3, x plus 3, and x minus 3, divided by x plus 3. After factoring out, you cancel out expression that can be cancelled out. The numerator and denominator have both x plus 3, so you can cancel out x plus 3, or x plus 3 divided by x plus 3 is 1. Multiply by x minus 3 gives us the limit of x minus 3 as x approaches 5. And this is now a linear function, and we can find the limit of x minus 3 as x approaches 5 by simply substituting 5 for x, or replace x by 5 minus 3 equals 2. Hence, the limit of this quotient or rational algebraic expression x squared minus 9 over x plus 3 as x approaches 5 is 2. In this example, we did not actually apply limit theorem 9 or the limit for a quotient of two functions, because we have simplified the given rational expression by factoring out this difference of two squares, square of x and square of 3, which simplifies this to x minus 3, which we get the limit of as x approaches 5, which gives us 2. If you directly substitute, if you directly apply limit theorem 9 to this will give you the limit of x squared minus 9 as x approaches 5 over the limit of x plus 3 as x approaches 5. And the result would be different from 2. And this is the correct way of evaluating this limit. Before you evaluate the limit of a rational expression, check if you can simplify the given rational expression. If you cannot, then you apply limit theorem 9. As in example 2, we have the limit of e to the x over ln of x minus 2 as x approaches 1. Neither the numerator nor the denominator can be factored out or simplified. Hence, we apply limit theorem 9 to the limit of the quotient of e to the 2x and ln x minus 2. And by limit theorem 9, this is equal to the limit of the numerator, limit of e to the 2x as x approaches 1 over the limit of ln of x minus 2 as x approaches 1. To find the limit of e to the 2x as x approaches 1, replace x with 1. And we get e to the 2 multiplied by 1. To find the limit of ln x minus 2, replace x with 1. We get ln of 1 minus 2. 2 by 1 is 2, and we have e squared, or e to the power 2. Divide by ln of 1 is 0, minus 2, or this gives us negative 1/2 of e squared. E raised to 2 divided by 0 minus 2 equals e squared. This is actually e squared minus 2, which can be written as negative 1 over 2, 1/2, multiplied by the numerator e squared. In this example 2, we apply the limit the limit theorem for limit of a quotient, where this limit of this rational expression is equal to the limit of the numerator divided by limit of the denominator as x approaches 1, which gives us negative 1/2 times e raised to 2. We will now state the 10th limit theorem for the limit of a quotient and whose limit does not exist because the limit of the function in the denominator of the quotient is 0. We apply limit theorem 10 to this example. Evaluate limit of x squared minus 2x plus 1 over x plus 3 as x approaches negative 3. In this given, the function f sub 1 of x is the numerator. So f sub 1 of x is x squared minus 2x plus 1. And the function in the denominator f sub 2 of x is x plus 3. And we get the limit of f sub 1 of x as x approaches a. This example a is negative 3. We get the limit of the numerator x squared minus 2x plus 1. And this is a quadratic expression as x approaches negative 3. And by a limit theorem, the limit of a polynomial function is obtained by evaluating the polynomial expression at this specific value of a, negative 3. So to find the limit of x squared minus 2x plus 1, substitute negative 3 for x and simplify. We have negative 3 to the power 2 minus 2 times negative 3 plus 1. And this simplifies to square by property of exponent. Square of negative is positive times square of 3 is 9. Negative and negative is positive. 2 by 3 is 6 plus 1. And the sum is 16. This is our L in theorem, limit theorem 10. L is 16. And the limit of the numerator, x is. The limit of f sub 1 of x is L as x approaches a, which means the limit of the numerator x is. As in this example, f sub 1 is x squared minus 2x plus 1. And the limit of x squared minus 2x plus 1 as x approaches negative 3, x is. And it is equal to 16. Now we get the limit of the function f sub 2 of x in the denominator. In this example, f sub 2 of x is x plus 3. And we get the limit of x plus 3 as x approaches negative 3. X approaches negative 3. And this gives us, to evaluate the limit, replace x with negative 3. We get negative 3 plus 3 equals 0. So the limit of the function in the denominator is 0. And the theorem 10 says that if the limit of the numerator exists, but the limit of the denominator is 0, then the limit of the quotient of the two functions, the function in the numerator and the function in the denominator, does not exist. The limit of x squared minus 2x plus 1 as x approaches negative 3 exists and is equal to 16. But the limit of x plus 3 as x approaches negative 3 is 0. Therefore, we conclude by limit theorem 10 that the limit of this rational expression does not exist, because the limit of the function in the denominator x plus 3 as x approaches negative 3 is 0. And the limit of the numerator x squared minus 2x plus 1 as x approaches negative 3 is 16. And we cannot divide 16 by 0 because division by 0 is not defined. You can also try simplifying this rational expression by dividing the numerator by the denominator. But you will get a term in that quotient whose limit is not defined. And so the sum of the limit of the first and second terms plus the undefined limit is not defined. We state and apply the last two limit theorems. Theorem 11 says the limit of the nth root of x as x approaches a is equal to the nth root of a. X here is replaced with a. And the limit of the nth root of x is the nth root of a. But there is a condition: a should be positive, greater than 0, or equal to 0. And we have this condition because in the set of real numbers, the nth root of a negative number does not exist. In limit theorem 12, we have limit theorem 12 is the generalized form of limit theorem 11, where in limit theorem 12 the function f of x is now x in limit theorem 11. So in limit theorem 12 the function f of x can be any function. The limit of the nth root of f of x as x approaches a is equal to the nth root of the limit of the function f of x as x approaches a. Again, there is a condition that the radicand, the expression inside the radical sign, the limit of f of x as x approaches a should be positive or 0, because we do not have a root for negative numbers in the set of real numbers. We take an example to apply these limit theorems. Evaluate limit of the cube root of 2x cubed plus 5x plus 11 as x approaches 2. In limit theorem 12, your function f of x is 2x cubed plus 5x plus 1. And your a is 2. And by limit theorem 12, this is equal to the cube root of the limit of the radicand, or the expression inside the radical sign, the expression inside the radical sign, or the limit of f of x. This is your f of x, 2x cubed plus 5x plus 1. And we get its limit as x approaches 2. Limit of 2x cubed plus 5x plus 1. And applying one of the limit theorems before, to get the limit of this cubic expression, replace x with positive 2. And we have cube root of 2 multiplied by, replace x by 2, 2 to the power 3. 2 multiplied by 2 to the power 3 plus 5 multiplied by x is 2 plus 1. And this gives us the cube root to the power 3 is 8, multiplied by 2 from outside is 16. 5 by 2 is 10, plus 1 is 11. And 16 plus 11 is 27. Is equal to cube root of 27, and the cube root of 27 is 3. Hence the limit of the cube root of 2x cubed plus 5x plus 1 as x approaches 2 is positive 3. We will now take an example for obtaining the derivative of a function. We start with algebraic functions using the definition of derivative that in turn uses limits for getting the derivative of a function. Consider the following example. Differentiate y equals negative 7x plus 3. To differentiate y means to find the derivative of y equals 7x plus 3. For this example, we will differentiate y using the definition of derivative of a function. Although there are differentiation rules for obtaining the derivatives of function, but for now we will use the definition of derivative of function using limit. And the definition says the derivative of a function of the form y equals f of x is given by the derivative of a function y equals f of x is denoted by y prime, or you can also use dy dx, small d over dx, or you can also use capital D, derivative of y with respect to x. But I will use y prime for derivative of y with respect to x. And by definition of derivative using limit, y prime, the derivative of y equals f of x, is equal to the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0. This is the derivative of y equals f of x, y prime. It's equal to the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0. This is the derivative of y equals f of x by definition of derivative. And this definition makes use of limit of function. In this definition, our f of x is negative 7x plus 3. Our f of x is negative 7x plus 3. And from this function f of x, we obtain f of x plus delta x. F of x plus delta x. So to find the derivative of a function y equals f of x, using this definition of derivative of function, we need the function f of x, which is given, and from the given function f of x, you need to obtain f of x plus delta x by replacing x in the given function with x plus delta x. In this function f of x, replace every x in the given function with x plus delta x. And we get negative 7. Replace x with x plus delta x. Plus 3. And simplify, multiply each term of x plus delta x by negative 7. Negative 7x. Negative 7 by positive delta x, negative 7 delta x. Plus 3. Now substitute f of x plus delta x equals negative 7x minus 7 delta x plus 3 in the definition of derivative, and also substitute the value of f of x equals negative 7x plus 3. So this becomes y prime equals limit f of x plus delta x is negative 7x minus 7 delta x plus 3 minus f of x. F of x is negative 7x plus 3. Because it has two terms, we write this in open close parentheses, negative 7x plus 3. In the middle term, we have a negative sign. If you have a negative sign and you want to take the negative of more than two terms, you write that expression with more than two terms in open close parentheses. Divide by delta x as delta x approaches 0. And this simplify the expression in the numerator by removing the grouping symbols. You have negative 7x minus 7 delta x plus 3. Now multiply each term. Negative 7x plus 3 multiplied by negative. Negative by negative 7x is positive 7x. Negative by positive 3 is negative 3. All over delta x. Check the numerator and cancel out the terms that can be cancelled, the terms that are the same quantity but with opposite signs. They will add up to 0. Like negative 7x plus 7x is 0. And 3 minus 3 is 0. And this simplifies to y prime equals the limit as delta x approaches 0. The only term left in the numerator is negative 7 delta x. Negative 7 delta x. And divided by delta x in the denominator. And you can see you have delta x divided by delta x. It will cancel out, or it will give the quotient top 1. Cancel delta x over delta x. And y prime equals the limit of negative 7 as delta x approaches 0. And you apply the limit theorem for the limit of a constant. The limit of a constant like negative 7 as delta x approaches 0 is equal to the constant, negative 7. Hence, the derivative of the given function y equals negative 7x plus 3 is negative 7. And we write y prime equals negative 7. In the next lesson, we will take more examples for obtaining the derivatives of functions using the definition of derivative that in turn uses limits. And for your practice, try the following exercises. Differentiate, that means you get the derivative of the given function. The derivative can be denoted by y prime dy dx or capital Dy sub x. And in these exercises, you will use the definition of derivative that uses the limit of function. In the definition, the derivative of a function y equals f of x is given by y prime equals the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0. In number 1, we have y equals 3x plus 5, and you get the derivative of this, denote it by y prime, and use the definition of derivative. In number 2, the given y equals 3 minus 2x. Your f of x in number 2 is 3 minus 2x. And find the derivative of this using the definition of derivative. These exercises are very similar to the example we had earlier. If you have question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalison. Thank you.